Hello everyone, welcome to this KANPUR-NPTEL online course on space environment and its effects on orbital spacecrafts. So, as we are going through this course, so the first few weeks, that is I think first 3 weeks, we focused on the solar activities, followed by the spacecraft system and its various segments, and then we discussed various types of satellite environments, namely the vacuum environment, then particulate environment, neutral environment, plasma environment and the radiation environment. And we have seen how whether the physics and how those environments affect the performance of the spacecrafts. Now, why we discussed all those things, just to know what are the risks associated with the spacecraft orbital environment, different types of environments. So, when this question of risks comes, then we should know how to do the risk assessment, and along with the risk assessment the term the reliability is also very important. So, in this module we will discuss the especially the what is the reliability, and before that let us have just a quick recap of this whatever we have just studied about the space environment effects. So, we have seen whenever this the environment is the vacuum means the particle density is so low. So, virtually there is no atmosphere there, and because of that the effect is the outgassing. So, we have seen what is the effect of the outgassing, then the thermal challenges, because here the heat transfer mechanism, it restricts only two types, that is the radiation and convection is not there. Then because the atmosphere is not there, the normal atmosphere is not there. So, there is extreme temperature that is from minus 150 to plus 150 degree, and this causes the thermal stress and the material fatigue. Then we have seen when we considered the neutral environment, we discussed the atomic oxygen, especially the atomic oxygen is it is of relevant in low Earth orbit, and as a result of the atomic oxygen attack, there is the erosion of the spacecraft surfaces, and this erosion creates many problems for the spacecraft materials. Then we have seen the hypervelocity impacts of the micrometeorites or the orbital debris, which can cause to surface damage and the penetration risk. Then we discussed the plasma environment, and in the plasma environment we discussed about the main effect of the plasma environment is the spacecraft charging, which is the surface charging and internal charging. And as a result of this spacecraft charging, we have the effect of that is ESD, electrostatic discharge, then the electromagnetic interference, there can be the physical damage because of the overheating, and because of the disruption of the communication and the navigation system, there can be the loss of the satellite. And the last environment which we discussed, it was the radiation environment, where we have seen how the solar particles events or the cosmic rays as well as the trapped radiation belt charge radiation belt, this means the Van Allen belt. So, all those things, and we have seen that there is the degradation of the electronics, then single event offsets, all those things we have seen. Now, in this session we will start discussing that whatever we discuss the space environment, we need to simulate those environments on the ground for the purpose of the testing and to understand how the spacecraft and the spacecraft materials or the subsystems they perform in those the environment. It is needed that we should assess the performance of the spacecraft while it is on ground by creating the space environment as well as the launch conditions. So, for that what is needed, that is the test and evaluation, and the test evaluation is done by creating the this space environment or simulating the space environment, and this is needed for the space qualification. Means once it is qualified, when it is tested successfully and evaluated successfully, then you can say that those components and those subsystem will work satisfactorily in the space environment. So, in this regard, this is we will introduce the term that is the reliability, and in this module we will just continue with understanding and studying various aspects of the reliability engineering. So, today we will just start with the reliability and the failure function. So, before I start this, it is important that to understand this topic, that is the reliability, this basic knowledge of the probability theory as well as the random processes are very essential. So, I request all of you to go through those the basics of the probability theory as well as the random processes, because this will refer again and again throughout this module. Now, what is the test and evaluation for space qualification? What is the objective? So, it is to ensure that the spacecraft components and systems meet the rigorous standards for the space environment condition. We have seen what are the the adverse space environment conditions. So, like the extreme vacuum, then radiation, atomic oxygen attack, temperature swings, vibrations. So, in order to evaluate for all those environments, the test and evaluations are done to verify the reliability, safety and the performance before you launch the spacecraft. So, various test and evaluations are carried out. So, I am mentioning here the basic test which are needed. So, the first one is the thermal vacuum testing, or it is also called TVAC testing. So, what is that does? It simulates the vacuum and the temperature extremes of the particular space environment. Then the next is the vibration and the shocks testing. Through these testings you simulate or mimic the launch stresses and the mechanical shocks. So, there are different types of the shocks whenever the stages are separated and whenever the spacecraft is injected into the orbit from the launcher. So, during those times there are various mechanisms that already we discussed those mechanisms, and during that the operation of the mechanisms, there can be a lot of the shocks generated to the spacecraft. So, you need to test all the subsystems. So, this is the objective of the vibration of shock testing. Then there is the radiation testing that we discussed in our last session. So, through radiation testing you check the components which are resilient, or if whether it is resistant to the space radiation or not. Then this is one important testing is the electromagnetic interference or compatibility, also known as EMI/EMC testing. So, this testing ensures that no harmful interference between the systems. And all these testings they follow some the protocols, and almost all the whatever space agency, if you consider NASA, ESA, ISRO or other space agencies, almost the protocols are the same. There is not much difference so far as the the qualification is space qualification is concerned. So, why we need this test and evaluation? So, the test and evaluation ensures the mission success and safety. What is the evaluation and validation process? So, through this testing and the evaluation process, the data enormous data is collected and its performance matrices and the failures. So, all those data that is the detail the data or detail the performance that the database is formed. So, which gives you what is the performance, whether any failures are there or not, and those data that is used to analyze to confirm that the design margins, whether there are design margins are there or not, and the tolerances are there or not. So, that you can ascertain whether the system will work or not. Suppose if there is some failure, then there is this is iterative. So, it is redesigned, then it is refabricated, and again it is the retestings are done. So, through this you can prepare a final qualification report and which will give the certification for the flight readiness. So, the test and evaluation is very much related to the reliability engineering. For the reliability, we need the data, and the data of the performance, that is the ground test simulating the space environment. This data is used as the input to the reliability. So, to understand whether this you have achieved the quality and it is whether the quality is assured or not, for that we need the data, and the data we get through test and evaluation. So, the space qualification test that verify that the components can survive and function in space, which directly impacts their reliability. So, this is important. We will define it mathematically what is reliability. So, reliability engineering, it involves the predicting and improving system lifespan and failure rates. So, we will see it is how this is done, and as already I said, the space qualification, the testing, it provides the empirical data. So, based on that data you can predict whether your system will work for whether the designated life or the desired mission life, whether the component subsystems, whether it will work or not, that only the space qualification data. So, that only gives that empirical data. And when you do this type of test and evaluation, so it gives, that is the enough input to understand the failure mode identification. So, this test it reveals, that is the test and evaluation, the weakness and failure modes that might not be apparent in design or simulation alone. So, only by simulation and design it is never possible to understand what is the weakness. So, in order to reveal the the inherent weakness, or there can be some workmanship problem, all those things are possible to reveal whenever we do a detailed or the robust test and evaluation. So, the reliability engineering uses this information to mitigate risks and improve designs. So, this is the main the objective of the that is the reliability and quality assurance. So, it is based on data driven decision making. So, test and evaluation generates data on performance, degradation and failure rates. So, in short I can say this, and this data feeds reliability analysis tools that we will see, that is it can be mean time to failure. There is another term called mean time between failures, and then FEMA. So, it is failure mode and effects analysis to predict future behavior and inform maintenance and redesign. So, that is why this particular activity, that is the reliability, or this particular the branch is very important, because without that thing the performance, you cannot guarantee some performance, or you can just have that confidence. So, the confidence is only possible through this detailed test and evaluation as per the reliability guidelines. And this already I said, that is the iterative improvement loop. In case of any failure detection, it is redesigned, then it is refabricated, and the retesting is done, so that it the reliability engineer's goal is achieved through continuous improvement. So, thus the space qualification acts as a practical reliability validation steps before launch. So, now we will discuss reliability in. So, how do we define the reliability? So, reliability is the ability of a spacecraft system or component to perform its required functions consistently without failure over a specified mission duration. That is important. There is always the satellite or the spacecraft, there will be a designated mission, there will be a mission life, and mission life is decided by what is the resources in the spacecraft, especially that is the control system, especially until unless you are not able to control the spacecraft. So, for that we need various types of resources to do the attitude and orbit control system. So, one is the onboard propulsion system. So, all and the propulsion system, if it is a chemical propulsion system, then the what is the propellant you are using, and that will have a a particular this you cannot have infinite quantity. So, that will decide the spacecraft or the mission life. So, basically this is the definition of the reliability. So, quantitative reliability prediction, it is based on the probability and the random process theory. So, I request all of you to go through or just to revise this probability and random theory. Of course, you will mention whatever is we are going to do, but it is better to have a just to revise the theory. So, here we are going to discuss the reliability function, then failure rate and the mean time to failure. So, there are few terms, very important terms in the reliability engineering. One is the reliability, the next is the availability and the maintainability. We will see how these three terms are relevant when you consider that is the reliability of a spacecraft or a space system. So, how do we define the reliability using the probability theory? So, it defines the reliability is defined as the probability that an item will perform a required function without failure under stated. Here the conditions I mean that is the environmental conditions, environmental and launch conditions. For a stated period of time, that is called the reliability. So, the reliability of a complete satellite system, it will depend on the reliability of its three principal constituents. So, the first is the satellite, the reliability of the satellite, then the launch vehicle, that should be the successful launch, and then the ground stations. Because this satellite operation is done through the ground station for data downloading or the telemetry, the tracking and telecommand, all those things. So, if the ground station is suppose it is not functioning, then you will not have the availability or you will not have the satellite services. So, now the next term which I said the availability. What is availability? Availability is the ratio of the actual period of correct operation of the system to the required period of the correct operation. So, this is called the availability. Now, let us see how what is the factor on its availability depends. So, the availability of a complete satellite system depends not only on the reliability of the constituent system, but also on the probability of the successful launching. Okay. Like as for example, if you consider navigational satellite, so we need the constellation of the satellite. Suppose if there is launching failure, so that that you will there will be some shortage of the satellites in the constellation. So, the availability, it depends on the serviceability, it depends on the successful satellite launching. Then the replacement time. What is the replacement time? Suppose some satellite has gone to its end of life and it is no more operational. So, what is that replacement time, or suppose in case of any satellite has failed, what is the replacement time, and the number of operation and the backup satellites, that we will see all those things whenever we will calculate the availability of particular satellites, but these are the things. So, availability with the ground stations depend not only on the reliability, but also on their maintainability. So, here for the ground stations, both the reliability and maintainability will be coming, because it is we can, it is in our hand, we can do the maintenance, but if the proper maintenance is not done, then again the availability will not be there, because availability is a function of the maintainability. For the satellites, the availability depends only on reliability, since the maintenance, that is if some suppose some power system or some of the subsystems is not working, then there is the current technology, using the current technology we cannot replace that system, or generally it is not done also, seeing the cost of the replacement or the repairing. Okay. So, now let us see this matrix quantification of reliability. So, this is a term which we are going to derive the expression for this, that is the mean number of failures in a given time, that is called the failure rate or the hazard rate. Then the mean time between failures. Of course, this is for items which can be repaired and then the system is returned to use. And then mean time to failure. So, mean time to failure, that we will use it for our satellite. This is meant for those items which are not repaired or as the portion of the total population of items failing during the mission life. We will derive the expression for each of this the quantity. Now, let us see what is the probability of survival or reliability. So, the reliability function we will use the symbol, or this is here it is a random function or it is a random. So, t is variable and R t will be t is a random variable. So, R t is a random function. So, it is also known as survival function S t, and how it is defined. So, R t is equal to S t, both are the same. So, R t is the probability that a unit survives beyond time t. What does it mean? That at time t, this is it is functioning. So, let us suppose that an item, it can be a component, device, or it can be a subsystem, is new, that is at time t 0 and fails at time capital T, and this is a continuous random variable here. So, whenever we say this in the probability theory, random variable or random function, it can be discrete or it can be continuous depending on the, that is the type of the variable. Okay. So, you can just revise those things, but here the time is a continuous random variable. So, here this t it has to be greater than 0, because it takes only the positive values. So, this item, now whenever I consider this failure or the what is the whether it is working or not working, there is only two states, that is the working or fail. So, in this case, whenever this is the case, there are only the two states, either success or failure or yes or no. Then the probability distribution functions we used in case of the using a discrete random variable. So, this is the binomial distribution function. So, I can use a term f some t is equal to p to the power k, then 1 minus p n minus k. So, this is called the binomial distribution function. So, where t is equal to k. So, what does it mean? That you for n number of trials, if you are getting the k successes. So, this is represented by this distribution functions, and if you want to calculate the expectation or the mean. So, that mu will be that is the mean is equal to n p, and the variance is n p into 1 minus p. Okay. Now, if when n tends to infinity and p tends to 0, with n p is equal to constant is equal to lambda, then this we can say this this distribution, it takes the form of a Poisson distribution. So, Poisson, I can write it Poisson k, and this expression is So, this will be so these are the two, or there are various other distribution functions will be used, but when I am saying there are two states. So, basically it is a binomial distribution, and binomial distribution in a special case when the sample size, in case very large sample size, we can represent it by a Poisson distribution. So, the reliability function R T, we can define it like this. So, this is called a cumulative the probability function. So, where T is greater than T. So, T is the what is capital T? Capital T is the time at which the device will fail. So, R T is the probability that item is still working at time T. So, what does it mean T? That is the probability of the that is it is still working. Now, there is another function, it is defined, this is called the unreliability function F T. So, unreliability or probability of having the system in a failed state F T at time T, failure has occurred between 0 to T is the complement of reliability. So, we will what does it mean that that is if this is the the reliability means here it is operating provided that that it will fail at a time t and here this t is less than capital T. But in this case it is t is between 0 to t. In that case, since this function this is the complement to this, then we should have the total probability should be equal to the 1. So, I can write R T plus F T is equal to 1. Then we define a failure probability density function. So, basically this probability density function we use in case of whenever it is a continuous random variable, and we can write this as the f. Now, I can write F T as. So, F T I can write. So, probability density function is defined as the whenever you have the cumulative distribution function, you differentiate it and if you differentiate it you will get. Now, you see if you differentiate this with respect to t, then d of R T by d t plus d of y d t, this will be equal to 0. So, you can write F T is equal to minus d R T by d t, and the probability of failure occurring a time interval t. So, you can write suppose there is a probability of failure that occurs between 0 to t. So, you can write it like using this expression. So, it is integration from 0 to t f u du, and if you take this total time, that is 0 to infinity f of u du, then this will be equal to 1. So, this is this is the total probability. So, it has to be 1. So, if you integrate this probability density function from time 0 to infinity, so it has to be equal to 1. In the next session, we will continue from here, and just I will stop here. Thank you very much.